Alright, welcome back to the second part of the assembly tutorial for Snake. In the last video we created the playing field and we initialized the snake, and today the goal is to make the snake move. So I hadn't had a chance to watch the video yet, so I am hoping everything worked, but if we have any errata, this is gonna take for another video, or we gotta figure it out today together. So I have my notes. We're definitely gonna need them. Okay, so let's go into not now, anything not now. Where is our cheat sheet? So the thing that we're gonna do, we have our snake somewhere on the field. Actually, let's see that everything is still working. So that's our snake, and now the goal is to make it move. So how do we do that? Well, the way we actually gonna do that is we're gonna take the symbol and we're gonna add it at this position. And I will not learn today to use the replace modem. So we go here, we go to the next, we replace it with a pound. So now it's 5 long, we go to the beginning and remove it with an empty space. And I think I could even do this with a Vim script here. Beginning, remove space, go one forward, Q. And now every time I execute the script, we would move forward. So that's the goal now, to do that. So last time we stored hopefully the snake in our circular buffer. So we have the head pointer and we have the tail pointer, and now the goal is to get the coordinates, move one forward and update, create a new pointer, and then take the tail and chop off the tail. So let's write that out actually well, let's do two things. Let's go ahead and declare our move function, snake, and move snake. Here we're gonna do a little boilerplate here to get us into the mood. Push Q, move Q, RSP into RBP. And then we're gonna do the same thing as always. And we're gonna do a pop Q, RBP, and we're gonna return. All right, so the goal now, we're gonna check if we are compiling here. Okay, so the goal now is, like I said, the first thing is we're gonna do is get the head pointer. Get the head pointer. Oops. Number 2 is get the coordinates from at the pointer. So get coordinates of head. Then we're gonna go ahead and say update. We update the head pointer. We can say this: get the head pointer, get the address it's pointing to, if we want to make this distinction here. It's a little too cold. Get the coordinates of the head from the circular buffer, then update the head pointer. In other words, add 2 to it. So let's say add 2. And finally, we're going to go ahead and not finally, then we're going to do update the coordinates. So if we are going in X for now, X plus gleich 1, plus equal 1. Alright. And for x direction. So that's the one for the coordinates, and then we need to store store new coordinates. 6 is dot and store new coordinates in circular buffer. Circular buffer. Then 7 is going to be get the tail pointer. No, if we have the new coordinates, 7 is going to be actually update place, update piece on the field, or update, so add the symbol to the field, add symbol to the field, and then 8, get the tail pointer, get the tail pointer. 9 will be get the address at the tail pointer, if we may be that precise. Address at tail pointer. Then 10 is chop the tail off, and 11 is update tail pointer. Well, so you're gonna see this function in absolute Uncle Bob fashion. Does exactly one thing: it moves the snake one block forward. Clean code at its best. All right, so that's the idea, and well, yeah, let's get right into it. Let me get here my coordinates, and maybe the chocolate makes me warm. So from this morning. Okay, so we're gonna get the head pointer first. Move Q head rip into RAX. Let's get the head pointer, and now we get the no. That's actually all we do. We're gonna remove that, and we're gonna go more clean code here. And where's the tail pointer? Get the tail pointer, because we are cruising here. See, already 2 steps removed, and we're down to 9. So if I had chosen layer Q, I would have gotten the address of the head pointer, but because we have a move Q, we already have the address that's stored in the head in the RAX register. So these 2 steps can be done here on our x86 in 1 step. So now we're gonna move the 0 RAX in a register, and I have to check which I chose here, B low and C low. So I think move byte into C low and an offset of 1 D low. So we have the pointer, was our picture. We have our pointer here. This is pointing exactly on the X, really. If we are more precise with this picture, it would be pointing here. And that means the 0 offset gets us the X, and the 1 offset gives us the y coordinate. So let's say, oh, this doesn't work. Y coordinate of head, and then somehow it's even the old y coordinate of head. Let's do this. Oh no, we don't like tabs. 0%. And this here should be the x coordinate of head. So there was a problem I had when I first implemented this. There was still something in RBX and RCX. RBX? Well, I think that's, oh yeah. I have here, I have B low and D low, not B low and D low. RBX is normally volatile, so I should not do that. Yeah, we're gonna do that. I might change that again tomorrow because now I'm rolling with what we have. But normally you don't use RBX on x86. Nevertheless, I had the problem that there was something in, so we're gonna zero them out. Percent error, RBX, and the same BD. Now let me hear BC. That's what I had. C. So we're gonna zero them out. All right, so now we have the still same spiel. We had the x coordinate of the head and we have the y coordinate of the head. Okay, so now we can do, we could immediately go and add it to the field, or we're gonna update. Let's update the pointer first. Well, I should really check what I'm doing. I add the address and then, okay, so we add the x address. So let's do that. Change plus x address or coordinate. So this would simply be add byte. Now it's this way, a 1 to below. So now we have below a 1. We would do the same for y, but at the moment we don't do that. So let's take the y and add a 0 for doing nothing. So now we have the y coordinate in the x coordinate updated by 1, so we moved 1 forward, but we haven't stored it yet in the head. So the next thing we want to do is take the address, add head, and move add 2 to it. 2 because we have the coordinates in pairs of x and y. So we have move q $2 into add, what I'm doing here, add q2 to RAX. So now that we have that, we have updated the address, and now we can use the new address to store the new coordinates. So move B low into 0 RAX and move byte CL into 1 RAX. So in an ideal world where we make no mistakes, now we have the circular buffer. We took the pointer, we got the coordinate, we updated the coordinate, we moved with the pointer forward, and we stored the new coordinates at the new position. And now we store the new address. The final thing would be to move Q the new address RAX add to head rip. Right, so now we should have this. Okay, so we went off. Okay, so if that's all done correctly, we could now use BL and CL to update to use this. So we have this coordinate, we added X to this, so we should now have this, and should be able to place a new character here. So, where do we start? So let's get the address of the screen buffer. Q screen buffer rip into which register? I have no idea. What? I have no idea what's happening here, so bear with me. I think we used RAX. There's a lot of stuff going on in my notes there. No, we'll figure it out. So now RDE gets the width. So now we are again using the formula width plus 1 times y plus x. That's the whole time our thinking. So now we need the width plus 1. So we're gonna move Q $width plus 1 into RDE. RDE it is. And where is our y coordinate? Is in in C low. Why does it C? So this here should be C low. Y coordinate is in C low, so we have to, I don't know, if we override the RDE. Yes, we do. So I multiply Q, we take the RCX and put the multiply it with the RDE, so this would be this part, and then I guess we also gonna add RDE dx, and the x is RBX. So that, oops, a little comma here. Yeah. Oops. So now we have RBX in RDE, and now the only thing remaining is adding the symbol. And here, since we're on x86, we're going to do that in immediate mode. So we're going to just move byte symbol. I'm not even sure if we declared that, but I think, yeah, of course, we had the border. We have the border, so we place it into talk RDE. Error, there's a comma here. Nothing happened. So this is the one thing with functions, a very pesky little thing. If you have a function, they want to be called, otherwise nothing's going to happen. So let's also discover our segfaults. There it is. I'm not even gonna bother, we're just gonna run it and see in RDE. Register read RDE. We haven't added the address. Okay, we can live with that. And so we calculated the offset, but we need to put here the screen buffer. So we're gonna use RAX RDE, I think. Should definitely check that now, but that's it. So did we do this here as well? Move thing symbol RDE. Oh, I added here. Well, actually, I like this better. So let's keep it this way. So now we have added the part here, and now we only have to do is, because the snake is only 4 parts long, we have to chop off the tail. So off we go. Chop off the tail. So where is the tail? The tail is all the same now, right? We have here, we got the head, we get the coordinates, so all of this, oops, we're going to do the same. Chop. I'm going to copy this here. So we have the head, but instead we use the tail now, and also here update the comment. So we have B low and C low should have the tail pointer now. And now we can also do this as the same thing. We need the screen buffer, we need to do the width+1 calculation, we add, and then instead of adding the symbol we do the empty space. Alright, see it? And that's it. So now we have added the piece and deleted the piece. So 1 second, we have done, well, not so fast. We haven't done, have we updated the tail pointer? No. So we need to add 2 to the RAX register at one point, and we knew that after we got the coordinates. So here we got the coordinates. We add 2 to RAX, and then we're going to store RAX in tail. Tail. So this should, now we should have done everything. So again, imagine the 2 pointers. We take the coordinates from this. We have the address, we go to the address in the coordinate pointer, we get the coordinates, we update the coordinates, we move forward with the pointer, we store the coordinates in the pointer, we get the coordinates from the tail, we update the playing field, and then we move it forward. Here I forgot to say, we update, once we have the coordinates, we use them also to update the playing field. Right? But yeah, that's the same. So if we didn't forget anything, which is unlikely, and we call this function now repeatedly, it should move forward, and it does. That is beautiful. So that's the video for today. No, that's not the video for today. The hard part comes now. So let's keep on adding here, because at one point we're gonna reach the boiling point. Two more. And we're just disappearing into the void right now. That's a thing which I suspect has more to do with our buffer size. Yeah, that was a buffer thing, so we are now touching. So let me go one back so we can see more drama without buffer interrupts. So we're one away. We move one step further. We touch. We move one forward. And now what's happening? That's the question. Nothing. Looks good so far. Did I do it? So now we move another one forward, and now we overrode the \n character. This one, the second row came up, and our snake is printed here in the buffer, and we have a problem. So how do we deal with that? First we check again if the camera is working. Okay, not twice in one day. So now we have to figure out what to do. And luckily for us, the x86 has a mod function. So that's taken care of. However, we have a few issues here. So, what up? Welcome from me in the future. You've just reached the point in the video where we made the snake move, went all the way through the border, erased the \n character and erased the line. So you should be right about here. The next step was to do the modular function. Actually not, because on x86 now we have the modular function, but we need a modular range function. And on the ARM version I didn't do a very good explanation, and I just did a re-recording of that part, and I thought a little bit spilled over in the x86 version, which I recorded right afterwards. So we're gonna do a quick errata here as well for the x86 version. It's just one function, and then I'm gonna give you back to the version from 2 days ago. All right, so having said all of that, let's go to what the modular function is. Now if I'm gonna get my head into this. On x86 we have a mod function. If we do a divide by register function, we have the RAX register and the RDX register. And if we are not doing unsigned division, we are erasing the RDX register and put our divisor in the RAX register, divide by whatever else register, and then we get the result automatically in the RAX register, and the remainder goes in the RDX register. Now there is a way to do this in a signed version. However, this is normally not the best way to go because we would have to branch afterwards, and we're not going to do that. But that's the way to keep, that's the thing to keep that in mind. Let us talk 1 second about how the modular function works. So let's say we have something like 8 divided by 10. Then the questions, let me make this a little bigger. The question is, how often does the 10 fit in the 8? Well, in this case, this would be 0. And the mod function then says, well, what is the remainder? And the remainder in this case would be 8. Right? So if we take another example like 18, or let's take 16 divided by 10, this is obviously 1. So the 10 fits 1 time in the 16, and the remainder is a 6. Now if we add the divisor to the dividend here, so we are taking 26 divided by 10, then we get a result 2, but the remainder stays the same. And the same goes if we are adding another 10, we get another, we would only, the result changes, but the remainder always stays the same. And if you look at this a little bit, then you might see that if you have something like a mod b, that's the same as, well, let's do it for an example here. I just do 26 by 10 mod 10. Then that's the same as to say, well, we have the 26 here, and we subtract 2 times the 10, which would give us 26 minus 10, which is 6, right? That's the remainder. And what this 2 here actually is simply 26 divided by 10 and then floored, right? Because without the floor function, this expression would make no sense, because we had 26 divided by 10 times 10, the 10 cancel each other out, so we have 26 remaining, so we have 26 minus 26, which is 0. So the floor function makes this all usable, and this is the the way this goes. Now the floor function also acts in the right direction. So for example, if we have minus 2.6 and we floor it, that's minus 3. Right? And there's like always a little bit confusion with that, but it goes to the lower number. And minus 3 is public service announcement. Minus 3 is less than minus 2. That's important because this formula in general, if we have A mod B, I just downloaded the VS thing here, so I can actually show you the nice version I have here. A mod B, this is equivalent to A minus floor A divided by B times B. And the way I remember this always is to say, well, if the floor function is not there, then this formula makes no sense, right? And I just explained that. Okay, so, but this formula also holds for negative numbers, as it is. And I want to give this example this is tightly related to the Archimedean property, or as I know it, the Archimedean axiom. And what the Archimedean axiom says is, for all epsilon, well, I wrote it here down in a condensed form, for all epsilon greater than 0, and when you see this, you should always think for all epsilon greater than 0, no matter how small that epsilon is, and for every real number, and in your head you think for every real number no matter how big it is, and what the property says is there will always be a natural number n, so that n times that small number will be greater than the real number that you gave me. And I remember this vividly from when my professor told me this in university, or not me, but the class told this, and he said, he tried to give us a visual explanation, and he said, now imagine there's something JVD, and I had no idea what JVD means, and JVD was Berlin slang for ganz weit draußen, which basically they used for saying that it's like in the outskirts of Berlin, or it's like far away. So here in New York, think upstate New York. So even if you have that, and I give you a ruler, and in your head you say again, no matter how small the ruler is, and I give you a place in upstate New York or whatever, far away, then there will always be an amount of times I can take the ruler and place it consecutively next to each other, and I will surpass that number. And for real numbers, it's only the surpass property, because you're not gonna hit it exactly, but you're gonna be able to surpass it. And that's how real numbers are, or it's one small part of how real numbers are introduced in mathematics, in modern math for students, and that's the Archimedean properties. So why am I telling you all of that? Because if you look at this formula, n times epsilon is greater than 0, or you have this in mind that it's a small amount and you place this next to each other and you surpass the boundary, this is very similar, the modular operation. The only difference really is what we're asking here is we have one number and we have the floored division. So how often does it fit in without overlapping, or without going over the number? So we're saying we take our ruler and we place it consecutively next to each other up until the next time we would do it, we would be over the number. And that would give us the number right before the division. And then we ask, hey, what's the difference between the number given and our ruler placed consecutively next to each other? And here the length of the ruler is given by the division floored. Right, so I thought this is very nice, and I could tell the story of JVD, ganz weit draußen. Good, so now we have this, and this property, okay, this is also how I came here. This property also works for negative numbers, because the division is sign preserving. So if you have a negative number and we take our ruler, we're now walking into the negative direction. And for a positive divisor, the remainder will always be positive, because there's a finite amount of times we can take a positive ruler, a ruler with the length greater than 0, place it next to each other, and reach the number in the negative x direction or in the positive x direction. Okay, so for computers that's not the case, because, well, for computers not general, but for our way the mod function works on computers, that's often not the case if it uses unsigned division. And here we're using unsigned division because we are going to XOR out the RDX register. There's actually a way on x86 to sign extend the RDX register into RDX and then get the 2's complement number. But if you do that, you have to account for that later, and we're not going to do that. So, having said all of that, I have here one example where I use the negative numbers as an example. Just take -1 as an example, mod it by 50. We have the -1 minus, and then you have the -1 divided by 50, which will give you -1 because it's 0 point something, so it gets floored. You have a -1, and then you multiply it by 50, and you end up with -1 plus 50, which gives you 49, which is the value that you want. Now, what I just said with if you're using unsigned division, then you have the case that a -1 would actually be, because you know that in 2's complement, every register has a finite amount of bits, and in 2's complement, we're using half of the bits for the negative numbers and half of the bits for the positive numbers. And in an unsigned integer, we're just using all the numbers, all the bits for the positive numbers. So what happens if you have a -1? It's actually binary FFFFF, so 1111111 all the way through. And if you reinterpret this as a positive number, that's the biggest positive number you have. So it's pretty much 2 to the power of 64 minus 1. And if you would do the math here, so you would get 2 to the power of 64 minus 1 minus the floor of the division, and it turns out to be 15. And if you were to do this in the game function, then the snake would appear on the left side of the field, in the middle of the field, for reasons you now know but are not quite obvious at the beginning. So luckily, compared to the x86 version, compared to the ARM64 version, we don't have to write the modular function. We can just use the modular function, and we just have to write the modular range function. And that's what I'm going to repeat now. I don't know if I deleted it. Here's the old one, and I'm going to delete this one right now. Just 1 second. So what you see here, this was let me delete this as well. Okay. What I did here was I simplified. I should change it. Oh, okay. Did I mention this now? This is the problem when you record 2 videos of the same topic. Okay, we have the modular range, and what I did actually in the old version, which was I simplified this part here to this part, and this doesn't help us in programming. It helps here. It's a better math expression. It gives you here the boundaries, but it doesn't help us in programming. So I'm going to say something, and if I have to cut it, I cut it. But one property of the mod function is if you have is this property. So if we have the divisor and have the dividend is a multiple of the divisor, then the mod function will always be 0. That's not really what we want, because what we want is we have our left boundary and right boundary, and we don't want to go back once we reach the right boundary and go back to 0, because we would end up in the border. So instead of, do I have this now? Here. Instead of going from the value 0 to width -2, -2 in this case is because we have the left border and the right border. We want to go from 1 to width -1. And of course the value we are dividing by is still the same, so the inner playing field range stays the same, but we are want to specify that it's from 1 to width -1 and not from 0 to width -2. And once we go out on the left side, so we are going from 1 to 0 to -1, -2, we want to circle back to the right side of the field. And because, as I just said, the modular function in the way we're using it uses unsigned division, we would get the wrong value, because that's the example which I did say with the 15. We would first of all, we would use the wrong sign, and then we would use the wrong number, and we would end up in a place where you don't expect it. And the way to counter that is by simply using this property that we here already covered. If we are adding the divisor to the dividend, the remainder stays the same. So in other words, adding the divisor to the mod function is an invariant. And we're going to do exactly that. What is this? This is Chrome. Oh, we should not use so much power. Battery is crucial for us here. So we are going here. I have this right about here. So this here is the formula that should be valid. That's the function that should be valid for positive and negative number if the mod function was correctly sign preserving. So what we're doing is we say we don't want to go from 0 to width -2, but we want to have it from 1 to width -1. So we're first shifting everything to the left so we can do our mod operation. And once we have done our mod operation, we're shifting everything back. Okay, this is the way, and this should work, but it doesn't for negative numbers. And to do that for negative numbers, we add the width, which I just said is the invariant, right? So, and because we are going consecutively, this will work fine, and we can have our values. At the moment they become negative, we shift them back into the positive regime, do the mod operation, and everything will be fine. So the one thing I did noticed pretty much during the recording last time is if you simplify this expression here, x minus a, this is the shift to the left, and then plus width is the amount to account for negative numbers. If you take this amount, we are using this also for the mod operation. And because we're using it for the mod operation, it's better for us to put this in a register and use it twice instead of simplifying this. And then I have to do here some odd calculation to calculate -2a, when in reality that's only for the paper. So a lot of words. Let me check the camera, because last time I had a camera failure. Okay, we're good. So all that remains now is actually implementing the modular range function, and then I give you back to my miserable self from 2 days ago. All right, how to do that? Where are we? Okay, RDE. I think we just deleted the function, so let me delete this here. And I'm going to delete this as well. I'm going to write it new. So now we're going to write the modular range function. Let me just check here. Is something... Okay. So we're going, now we're coding. Okay, modulo range. It's oddly slow. Doesn't matter. Okay, push Q RBP. You're gonna move Q. No, something is not right here. Something is not correct. Okay. Maybe it gets better. So you're moving the stack pointer and the base pointer. And at the end we do the opposite. Let me check if I have... Do this. It doesn't react really. And now I don't know where I am. Or it's the sun overheating. So we moved the RBP in the RBP in the RBP. Now we move the RBP in the RSP, restoring the stack pointer. Pop. Pop. Q. RBP. And return. All right, no complaining. We are having the calling convention, so what we're going to do is the first thing is going to be an RDE. That's going to be our value. RSE is going to hold the lower bound, or A, lower bound. I'm going to place here in parentheses A. And RDX is gonna hold RDE, RSE, and RDXD. Upper bound. Oh, this is not what's happening now. Empty bin, yes. Is this a problem right now? Can I close this? And other than that, screen recording we need somehow. Otherwise, okay. So hopefully it's a little better. I don't know. Let me check one thing here. Oh, it's good. So the first thing that we do, now we don't have the formula. So let's write the formula down here. The formula is pretty much x minus a. That's the left shift. Then we add to this the width, which is b minus a. We're going to take both of these things and mod them by the width, so b minus a. And once we have done all of that, we are going to add the lower bound, which is a. So the first thing we're going to do is store this value that we need at the end in a register. And for now I'm just gonna use R8. So we're gonna move A is in RSE into R8. So now we have this, and I think the next thing we're going to do is calculate our value b minus a. And now I have to add queues again. We have move queues, now we're going to sub queue. And we're going to use b minus a. So in this case, we're going to get the result in b, which is going to be rdx, because we don't use b afterwards. So we're going to use lower bound is RSE RBX. RDX. Alright, and now I'm not gonna gamble on directions of assembly. So this is, I don't know why this is so slow right now. Move. Q, we're gonna move this into RAX. So RDX goes into RAX, which is the return value. Gonna go down here, comment out all of this. I'm gonna comment this part out, and then we're gonna just do a simple modular range example. And what's that gonna be? We're gonna move in RSE the value 7 into RSE. We're gonna move 1, the 1 in in RSE, and the 7 gets in RDE, and we have to move the upper bound goes in RDX. And we're gonna call modular range, and then we're gonna move Q RAX, which is the result, into RDE so we can see it. Now let's compile it. Move Q RAX RDE 369. This was right about here. I don't have the comma. Okay, so now we can execute it if he wants. I have to see the battery life here, okay? And let's see what we got is 49. So we have 50 minus 1 and got 49. Okay, so we did indeed calculate b minus a. So let us add a comment here for good measure. So this is now b minus a. I feel like the computer is getting, he got back from his hiccup. Now it feels really usable. And here we have store A. So now we have this part, and the next part we're going to calculate x minus a. X is in RSE, so we're going to overwrite this as well. We have, no, in RDE we have RSE minus RDE. RDE, no, like, okay, 1 second. So RSE is the lower bound, and we want to overwrite the lower bound, so I'm not going to trust anything at the moment. I'm going to put RDE, so x minus a should be, if everything works out, we are down here, we should 7 minus 1, we would expect a 6. So there's our 6. And we have this. So let me add a comment here as well. So this is x minus a. Okay, x minus a. And now what we will do is add these two together, and we want to have this result in RAX because that's the register where we need the dividend in. So we're gonna add Q RDE. Well, we're gonna go, we have to still add them, so we're gonna add RDE and RDX, and we need RDX, so we're gonna use RDX, RDE. So now we have in RDE here this part, our divisor. Come on, let's write a comment. So we have here x minus a plus b minus a. And this is, we're going to move that now in RAX because that's where we need it. And now we have the b minus a should still be in RDX, and that's the worst register to be in. So let's move RDX into RCX. And then clear out RCX. So now we have, not RCX, RDX. So we have RDX is 0. We have our dividend in RCX and our divisor in RCX and our dividend in RAX, and now we're gonna call diff q RCX. And now we should have the result. After this instruction, we have the result in RDX, the remainder. So we would have we want to add q RDX to, I cannot see if there is a sign, or comma, RDX to the sign we preserved, the A at the beginning, so let's do that as well. Add this to R8, and then finally we take the triple D out and move our result in the RAX register. That was a lot, so let's wait for our segfault or for our instructions. Move QRDE 65, 67. There's a comma missing, and XORG is XORQ. Okay, 67. Where was it? 65. Okay, we go here, and whereas the XORG is XORQ. Where's the segfault? No segfault? Okay, we don't even know what we want. We have now 7, so we want 7. That's okay. But now let's take the 1. The 1, that's the interesting point, because this is when the head's on the border on the left side. So what do we get? So that's 1. But now if we change it to 0, what do we get? $49. So the moment we hit the 0, the border, we are circling back to the right side. That looks good. Let's take the -1 as well. And let's see what it gives us. 48. So that's working perfectly. So what if we have a 49? Let's take this as well. We get the 49, but now we're hitting the width. And we have a 1. So we are circling in both directions. So the last part I'm now going to do is take that modular range function, copy it back into the file, and then give it back to my old self. So let's do that right now. Modulo range. Take the comments here as well. Jacket, split it, open snake x86.s, and then we're gonna modulo range. This is the part, and you see here the 2a function with the shift stuff. This is all gonna disappear right now. And now we have it here. I'm gonna save it, and I'm giving it back, and everything should be fine. We have our modulo range function. So now let's put it to use. Where is the move snake function? Remove snake function. Here we have to be careful now. So we have our head, and we have our x coordinate, and here we add the coordinate to 1 in the lower part, in the B register. So now what we need to do is we need what do we need? We need the 1, we need the width -1, and we need the value in RDE. So the first thing, let's move our, move Q RBX into RDE. Then the movement of 1. This is correct. Move Q of 1 into RSE, and move the width -1 into RDX. No, let's width. We are now in range, so we have width -1 is width minus, this is the 1. This is the -1 now because we are in range. And now we're going to call modulo range. And then we're going to say we have the result in RAX, and we placed it here from RBX. So we move RAX into RBX. So now the problem is that we probably lost CL RCX in the process, and I'm not a fan of pushing and popping, so I probably did something on the stack frame. Let me check that. Also, I should not say probably, we definitely lost CX. We used RCX in the modulo range function. So we're gonna make some space here on the local stack frame, sub Q, and I chose here 24. I'm not quite sure why, but I trust myself. Sometimes I trust myself. So we did this thing, and after the adding, I did this. Whoa. RBX, RDE, modulo range. Let's place this down. And store here before we do anything. Move Q RBX. I should maybe I will do that and name local stack frame. So RBP will get RBX for this, so this is the X coordinate, the updated one. Then RCX goes on -16, RBP, okay. And what did I update more? The address, oh, the head pointer. RAX in -24. I'm not quite sure why I did that. We will see that in a moment. Well, we need it right here when we store it, so that's why. Okay, so that's this, and now we have already done this part, and here I say width -1 again. So forget what I said. I trust myself when I tested stuff. So width -1 here. Why is it width -2? Because left and right border. Okay, so then we call model range and we move it RAX in RBX. Okay, and now we have to do the same obviously for the tail here, otherwise we don't even have to test it. So somewhere, well, no, the tail is, because the tail we are not adding something here, we are just going in the buffer. So if we updated the head coordinates correctly, the tail has the coordinates. So let's make the buffer here for a moment a little bit bigger. And let's, well, are we still commented out? Okay, so let's do that. Let's run it. Oh, the segfold, the best. Okay, LLDB, snake, and run it. But that's probably we have to load somewhere here. RAX, register read RAX. So here it's 1B, and it should be the address, so we have to store it before move B. So that's probably why I stored REX. So right about here, I guess. No, here we're adding it. Yeah, right here we need move Q -24 RBP into RAX again. And then we add to, I should check that with my notes though. Well, it's gone. And it's gone. And it's gone. Why is it gone? Well, we did the buffer thing. Did I where did I did it right? I wanted to see first in X direction. We moved it in X direction. We got the head pointer back, and then I added the 2. This is all for the other coordinates. We should here, well, we set this, we should here at least move -8 RBP, because we are storing here the coordinates. We are probably lost them right here. No, we're not. We lost them right there. So let's get them back. I thought RBX and I wrote RBX. RBP, and then here let's take the 16 in RCX as well. So now we should have our coordinates back. And we're moving, but we are still getting out of bounds. Yeah, but this is also stupid, because our BX is the one we don't want to recover. Right? Yeah, there we go. So if I do that, we should now move around. All right. But let me do, where were I? Here. So this is stupid, but we should do it the other way around. Jack till dup, or D till pop, 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 pop. And we're gonna store RB. We have the coordinate now, and we're gonna store it on the local stack frame. And we're gonna retrieve RCX, and now let's do the same thing here immediately with RCX, even though we haven't done that yet, but we trust that now because the function obviously works. Height RDX, and we call it Rx into RCX, and then we're gonna do the same here, this part. Wow. We have CX now, so we're gonna store our CX on the local stack frame, and we're gonna load BX because it was destroyed. Why is there no queue here? Why is it not complaining? I mean, I'm more surprised that it didn't complain. Low-key annoyed by it. So now we have the movement, and CX should be working. So the high-level gist is we update here our BX and CX, put it on the local stack frame. Then we do the modulo operation. For that, here we have the new BX, the BX in range. In the meantime, our C got destroyed, so we get our C back from the stack frame, and we store the B on the stack frame, the new B, with the mod. Now we do the C, same spiel. Our new C gets stored on the stack frame, and the old B was deleted. The B that we calculated here in this part of the code was destroyed, so we are getting it off the local stack frame again. So that's the whole thing here. Okay, so that's not too bad. Next we have to put the function to use in another way, and that is to make the buffer itself circular. So where is this happening? So we have to add somewhere a 2. So we add here the 2 to RAX, and that's we are trying now. Well, I guess we are destroying stuff. So we're gonna move Q -8 in RBP into RAX, -16 into RCX, And here we're going to do now our function call. So RDE gets our value, so we're going to move Q RAX into RDE. Now move Q. Now we're going to need the lower bound. The lower bound is just the address of the coordinates. So we're going to layer Q coordinates rip into whatever. Lower bound is RSE. And the upper bound is coordinates plus buffer size. And because of our layout, that has an explicit name which I'm going to use now. Undo, redo, undo, redo. So we're going to use the head in our dx. So we're calling the function now. We have the beginning of the buffer. We have, like in C++, the iterator points after the end. This is now our head, and now we do the modulo operation with the address that we have in RAX in our head. And then we should get it back in RAX, and we're going to put it on the local stack frame. Now we're going to actually store it in head. Not store. Move Q RAX on head rip. So this should be fine while it compiles. Do we dare it to run? Oh, we have a segfault. Look at that. Register read RAX 19 BLCL. This should be right here, I would guess. I did a mistake here. RBX. Aha, okay. So do I trust this? Yes. So let's do the same thing with the tail. Well, there's one more at $2 at Q $2 $2. Do I have to escape this? So this is what we just handled, and where is the tail? Add Q $tail. So this is pretty much the same thing, right? I hope we are not too far off the script in case we need to debug something. So we have RAX in RDE, coordinates and head. This stays all the same. And then we're going to store it in the tail. So this is all going to be here. And then we're going to move the new RAX. No, wait. Did we even call modulo range? Or did I just forgot the most important part here? Add Q call modulo range. That's kind of important. Segfault. Modulo range in head. Okay, LLDB snake. Move byte 20 in register read RAX screen buffer, that's fine. Register read RDE. Well, that's also not terrible. Well, it's probably too big. Where is this?
My mom is like, where are you now? It's after 5 p.m. and it will start to get dark.
Where are we? This is right here. So We stored it in the tail. We got the screen buffer. We have RDE, and REX should actually not be the problem, right? Where do we get the coordinates from RAX? No, that's fine. We get the coordinates because here we get the coordinates from the tailor. That's a valid pointer, and then we add 2 to the pointer. We move this in RDE, RSE, and RDX. We call modulo range, and we move RAX into the thing. But are the coordinates stored that we got here? No, they are not. Do we store them, or do we store them? I think we store them. So we're gonna move Q -8. We can reuse the local stock frame with RBX. No, we move. What am I doing? RBX in RBP, and we're gonna move our CX in -16 RBP, and then once we're done here, we're gonna retrieve them into RBX, and here into RCX. Oh, that's not make. That's that's make. Oh, we didn't crash. Okay. So now we can make a test here. We can make this small. And that worked. That's a good sign. That's a good sign, because that means the circular buffer works. Let me check again. Okay. We check the audio. Also, that's fine. So we have what we have. Now we're gonna write now really quick and dirty an improvised sleep function, so we can try to loop that. And why did I do that? So what are this? No, 15, 5. Just remove stuff here. Move snake. Oops, I deleted print playing field. Doesn't matter. Print playing field. So that's that. And now for the final step. Not the final step, but the next step. We're gonna write a very simple speed function, a sleep function. And I already set this in ARM. We're probably gonna replace them at the very end. But I think for the most rudimentary part, this is still a good way to do it. As it's not good because it makes we're gonna write a busy loop, and that's gonna make the CPU go brrr. But okay, let's do it. Push RBP. Is this correct? I'm not even, yeah. Move Q RSP into RBP. RBP into RSP. Pop RBP. RBP. RBP and return. And no bang to take care of. Alright, so we have to get a loop, a 1 into RAX or something, sleep loop, gonna jump to sleep loop. We're gonna have an end. Well, we probably don't need that. Sleep loop. So we have to do 1, 2. No, actually no. We're gonna go. We can do 1 space here, and now I'm gonna do a simple compare. Compare Q dollar. No. Yeah, well, dollar pound speed with RAX, and the moment that is equal, not branch, jump equal, we go to end sleep. Now we're gonna do end sleep function. It's not, if it's not necessary, it's like weird to have 2 labels. End sleep function. So we're gonna delete this label. We have end sleep function, and now we're just gonna add Q1 to RAX, and we're gonna add a few no-ops. I'm sure this should be okay. Do I have to no-op Q this? Compare Q speed. Oh, we don't have speed yet. Oh no. Not only do we not have speed, we don't have a value here. Oh. Okay, we have to hurry up here. Speed, and now I'm gonna check what speed I chose for this. 0x. This is just a hexadecimal value, which was okay. This is just a big value till which we count each time in the loop. Now we can test it here before we exit. Call sleep function. Well, I don't see much delay there. I'm not sure what causes the delay here and if this is working. So let me check that. I called it busy sleep loop. Otherwise, it's pretty much the same here. Oh, I did one thing differently, and that might be important. So I did the speed, I don't know, with the values in RBX, and then I compare RAX and RBX. X. So it might be that the immediate has a limit there. Okay, I don't know, so let's just try it. We're gonna initialize this, clear the screen. We need to call this down. We have the game loop, and we're gonna jump to the game loop. That's the idea. Oh. And it's running. Oh, okay. So this is gonna eat the battery, so we're gonna stop that for now. However, we're gonna keep on moving. So we have a sleep function. This is just, we're counting to a number, right? That's just a loop. We have the screen wrap, but we have to check plus X. What happens if we subtract it? Sub Q, this is now the sub Q, sub byte. Stop shaking here. It's Easter. Can't be cold on Easter. Okay, this works. I'm happy with that. And now the crucial part, what is if you go in Y direction? That works as well. And now one last thing. No, don't do that to me. Okay. It works in all 4 directions. Okay. That's encouraging. So let's for fun do this one. And let's have a diagonal movement of our snake. The only time we will ever see that. Okay, done. So, we need a direction. Do we have a direction? Yes. Do we initialize it at the beginning? Yes. Oh, we have still a few more minutes to go. So, let's do it. First things first. Let's do the glitch first. So, up until now, let's take a bigger buffer. I don't know, just for a bigger thing, and initialize the snake to 10. Okay, we are still having the diagonal snake plus X. So where is it? We're gonna go in add byte, and we're gonna go in X direction here first, just to make sure everything works, even with the longer snake. And that works. But now let's go in the Y direction. And we're going here, and there are like 2 or 3 spaces between the snake. Now let's increase that to 12. And now we go there, and we see there's exactly 1 space in between the snake. So let's do 1 more. Let's store it, and let's go. Here it goes, and welcome to the disappearing snake. So let's do that again. It goes down, and then it slowly disappears. Let's look at it one more time. Goes there, disappears from the bottom, then disappears from the top. Why is that? Well, we are very careful and conservative here. We are always adding, I should use replace the piece, and then remove it at the end. Now that we have screen wrap, the following happens. We have our snake here. So let's go here. Now if there is no element here, we would still add this one here and remove this one here. Add the new head here. Add the new head here, remove it here. And that's the way it would move down. However, now that we are exactly on the tail, what we're doing is we are adding one part. We are adding, I can't talk, I just can't smoke here. I don't even want to smoke, so that was the security guard was, yeah, it doesn't matter. So now we have the head directly behind the tail. So now what we do is we add the piece on top of where the old tail is, and then we remove the tail. So by removing the tail this way, we are removing the new head as well. And that's why we're going down, and we're slowly removing the tail when we are making this, when we're going around. So even with our conservative, careful method of first adding the head and then removing the tail, we have to accept that that's the wrong way of doing it. So what we actually want to do is first chop the tail off and then add the head. So let me go to chop the tail. Also, I didn't add. I should add, like, some comments are just necessary. So here, this is the real important part. This is chop, chop, chop. Also, I just realized, even though I'm using them, I don't have to use these comments. These comments also work. Okay, where are we with our tail pointer? So this is all tail code. We're gonna take the whole tail code, remove it, and add it before the head, somewhere here. This should be fine. So here we put the tail, store the tail, we chop, 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 and here we're gonna do update head pointer, or update head. That's enough. So, and if hopefully now it works. There's still not a lot that we see here, and for that reason we're going to now make a special head character. So let's do that next. EQ, I think, I don't know, symbol head or head symbol. I think I meant it's symbol head. Let me check. Low battery. Symbol head is 0x40. X40? Yeah, then go to sleep here. Wait till I need you. So up until now we're chopping we're moving the head. We got the coordinates out of the buffer, moved forward and added a new piece. Now assume, well, I should show this. Assume we have it this way. Replace 1, 2, 3, 4. Now replace, we have here our head. So now what we're gonna do is simple. We're gonna replace this head with a pound, then go forward, and then add a new head here one further. And that's all we're gonna do. So, what did I do? Okay, I don't know. Move snake. Move snake. We're gonna go to head. Chop the tail, the head here. This is the end address. So we update the head. Here we have to do this obviously before we update the coordinates, so somewhere here. But what we want to do here now, no symbol. So I have to think, where's my symbol? This is right here, and now here we're going to use symbol head. Is this the right word? Yes. And we're going to do this part here simply immediately after we got the coordinates. Right about, well, here. Screen buffer, do we have the screen buffer here? No, we have the head and RAX, and do we need, I'm assuming, oh well, I assume we need the head here, so we are gonna place the RAX in minus 24 RBP. And then we're gonna load it after the new choppy action here. Now we chop the head off as well. RAX. Let's see what's happening. Nope. Yo, that's not symbol head. Here we want to have the symbol. Well, it looks like it's working, but I'm not quite sure, so let's make it 4 again and make the direction plus X somewhere here. Let's make it X, make it 0, compile and go forward, and there we have our head. I think we have to do the initialization as well. Well, if you want to be precise. Low battery, okay. Not gonna be precise. I'm gonna finish one last thing. And that is, we're gonna make the directions here. So this is the last thing. This here is, as far as we know, move forward. We're gonna make move backwards. This would be subtract, sub b1, then we have, we don't need that anymore. The only thing I'm gonna need here is plus x, so I can look for it. We're gonna say move up. Well, we're not 1, 2, 1, 2, and now we're gonna do move down, and then the next thing that we're gonna do is we need the direction in a register. I don't know which one, or more or less what I chose to do. Direction. Oh, I haven't even done this in this version yet, so I need to open the right one. Documents. On REX. In RAX. Okay, symbol. Yeah, well, we store here RAX, so I guess it's fine to say move Q direction, rip into RAX, and then we're gonna say here compare Q1 with RAX, and if they are jump equal, not equal, we're gonna move to move backwards. And again, maybe we should do whatever. Maybe we should do here a switch statement, but for now this is fine. So if it's 2, if it's not 2, then we're gonna move up. And if it's not 3, we're gonna move down. And move down, we're gonna, I think up is sub here. Sub B, and we're gonna compare here also. So we're gonna say 4, then move, jump to end directions. And we declare the label here, end directions. And now here we're gonna load, we're gonna store everything here. That's RAX, move it in RAX. Well, we're gonna move Q RAX into -24 RBP. Okay, we're moving slowly. Oh, we lost it. Okay, So this is not happening. We're gonna finish right there tomorrow. So guess who's back? We have a little bit of battery life, so let us test this. I don't know, I think the last thing we saw was the last thing I typed, which was we're trying to get direction in RAX and check if the directions are here, and then we loaded the direction back. So let us check if we're even compiling. And we are moving weird, so we are not having, we just definitely destroyed something. Yeah, and this is, we are storing it, and here we have to load it. So let's hope that's all we had to do. Okay, we have like 30% battery life. Okay, that was the problem here. So now let us go to direction, and if we initialize it with 2, are we getting the value, are we getting what we want based on that? So we're going in the 2 direction. Let's go 1 around. Let's initialize it to 3. That should be up, and that's not up. So why? Oh, let us check this. Compared to 2, move down sub 0 from CL. Okay, that's already weird. And here we should add 1 to CL. Not quite sure why it shrink to a point. Oh, okay, we're moving up. And direction 4, be it down, and we're down. And now we do one last thing, reset it to 1 and watch it one last time go across. And that seems to work. So this wraps up today's effort. Tomorrow, well, in the next video, let's say it in the next video, we are going to make the controls work. We're going to go in the preview, documents, assembly snake x03. So this is the preview for tomorrow. So here I can now control the snake, and that's the goal for the next video. But we will do that tomorrow. So again, happy Easter, and thank you very much for watching. See you in the next one.